Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today we're going to be discussing intermolecular forces. This topic is super important because it helps explain why substances behave the way they do in the liquid and solid states. Further, these intermolecular forces are responsible for determining key physical properties like boiling point, melting point, and solubility. However, before we get into intermolecular forces, we first need to distinguish them from intramolecular forces. When we talk about chemical bonds, we are referring to intramolecular forces. These are strong forces that keep atoms connected within a compound. These forces define the chemical structure and stability of a compound, and there are three main types: ionic bonds, covalent bonds, and metallic bonds. Let's cover ionic bonds first. These occur due to electrostatic attractions between oppositely charged particles. In an ionic compound like sodium chloride, sodium donates an electron to chlorine, forming sodium cations and chloride anions, which are held together by their opposite charges. This electrostatic attraction is extremely strong, and it gives ionic compounds high melting and high boiling points. In addition, the bond strength of ionic interactions, they can range anywhere from 400 to 4,000 kilojoules per mole, depending on the size and charge of the ions involved. Next, we have covalent bonds. So unlike ionic bonds, which involve electron transfer, covalent bonds form when two atoms share electrons. This type of bonding occurs between non-metal atoms, such as chlorine gas, where two chlorine atoms share a pair of electrons to achieve stability. Covalent bonds, they can vary in strength, but they are generally within the range of 150 to 1100 kilojoules per mole. The exact bond strength, that depends on the type of covalent bond. Is it single, double, or triple bond? With a triple bond being the strongest and the single bond being the weakest. Finally, we have metallic bonds. These are found in metals, and these bonds occur when metal cations are surrounded by a sea of delocalized electrons. This free movement of electrons is what gives metals their unique properties, such as their conductivity, their malleability, and their luster. Because the electrons are not bound to a specific atom, they can actually move freely throughout the metal structure, which allows these metals to conduct electricity and heat efficiently. The strength of metallic bonds also varies, and it ranges from 75 to 1,000 kilojoules per mole approximately, depending on the type of metal and how tightly the electrons are held. Now that we've reviewed intramolecular forces, which are the strong forces within molecules, we can shift our focus to intermolecular forces. These are weaker forces that exist between molecules. Intermolecular forces hold molecules together in the liquid and solid states. These forces arise due to electrostatic interactions between molecules, meaning they depend on the distribution of charges or partial charges within a substance. The strength of these forces varies, which is why some substances are gases at room temperature, while others are liquids or solids. The stronger the intermolecular forces, the more energy is required to separate molecules from each other. In addition, these forces determine how molecules interact with each other, and they are, again, responsible for many physical properties like boiling point, melting point, and solubility. In this class, we're going to mention four main types of intermolecular forces. We will start with a brief overview on this page before we dive into a more detailed discussion of some of them in the following sections. To start, the strongest of these forces is the ion-dipole force. This occurs when an ion interacts with a polar molecule. A polar molecule is a molecule with a permanent dipole, where there is a partially positive and a partially negative end. Ion-dipole forces, they play a crucial role in solutions, particularly when ionic compounds dissolve in polar solvents like water. For example, when table salt, sodium chloride, dissolves in water, the sodium ions are attracted to the partially negative oxygen atoms in the water molecules, while the chloride anion, this is going to be attracted to the partially positive hydrogen atoms. This interaction is strong because it involves a full ionic charge from the sodium cations or the chloride anions, for example, interacting with a partial charge. Here, in this case, it's water. The strength of an ion-dipole force, it can range from 40 to 600 kilojoules per mole, depending on factors like ion charge, size, and solvent polarity. Next, we have hydrogen bonding. This is a specialized and particularly strong form of a dipole-dipole interaction. Hydrogen bonding, it occurs when a highly polarized hydrogen atom is directly bonded to a highly electronegative atom, specifically a fluorine, nitrogen, or oxygen atom. It has to be one of these three. These highly electronegative atoms, they create a strong partial negative charge which attracts partially positive hydrogen atoms from neighboring molecules, forming a strong intermolecular attraction known as hydrogen bonding. While hydrogen bonding is not as strong as ion-dipole interactions, they're still pretty significant, with strengths ranging from 10 to 40 kilojoules per mole. Moving further down in strength, we have dipole-dipole forces, which occur between two polar molecules that have permanent dipoles. So unlike ion-dipole forces, dipole-dipole interactions, they involve only partial charges, making them obviously weaker. In these interactions, the partially positive end of one molecule is attracted to the partially negative end of another molecule. Now, in these interactions, the strength of the force depends on molecular polarity, and the range for dipole-dipole interactions is usually around 5 to 25 kilojoules per mole. Finally, the weakest of all intermolecular forces are London dispersion forces. These are sometimes called van der Waals forces. So unlike the other forces we've discussed, London dispersion forces, they exist in all molecules regardless of whether they are polar or nonpolar. These forces arise due to temporary dipoles which form when electrons in a molecule or atom momentarily shift and create a brief imbalance in charge distribution. This temporary dipole, it can induce another dipole in a nearby molecule, leading to this weak intermolecular attraction. Since these dipoles are constantly forming and disappearing, London dispersion forces are the weakest of all intermolecular forces, typically ranging from 0.05 to maybe 40 kilojoules per mole. Now, something important to note is that London dispersion force strength increases with molecular size because larger molecules have more electrons, making their electron clouds more polarizable, and increasing the chances of forming stronger temporary dipoles. Now that we've explored both intramolecular and intermolecular forces, let's summarize some general trends. Even though the strength of these forces varies depending on the molecules involved, we can still establish some broad trends that are going to help us in our Gen Chem 1 class. We'll start with intramolecular forces. These are always stronger than intermolecular forces because breaking a chemical bond requires significantly more energy than overcoming intermolecular attractions. So among intramolecular forces, ionic bonds are the strongest, followed by covalent bonds, where triple bonds are stronger than double bonds, and double bonds are stronger than single bonds. Then we move into intermolecular forces. The general trend is this. Ion-dipole forces are the strongest because they involve a fully charged ion interacting with a polar molecule, and that leads to a strong electrostatic attraction. Hydrogen bonding is next, followed by dipole-dipole forces, and finally, London dispersion forces, which are the weakest, and they arise from temporary dipoles due to momentary electron shifts. Now that we've established these general trends, let's apply them to a couple of practice problems to test our understanding. The first problem asks, which of the following has the strongest intermolecular forces? To answer this, we need to identify the dominant intermolecular force that each substance experiences between its own molecules in a pure sample. The first answer choice is water. Water molecules exhibit strong hydrogen bonding because each molecule contains a hydrogen-oxygen bond that allows for extensive hydrogen bonding interactions with neighboring water molecules. Next, we have methane. Methane is a nonpolar molecule, meaning it only experiences weak London dispersion forces between its molecules. Next is carbon monoxide. This is a polar molecule, so it experiences dipole-dipole forces between its molecules, but not hydrogen bonding because the hydrogen atom is not present. Finally, we have helium. Helium is a noble gas, meaning its atoms interact only through weak London dispersion forces, and since it's a single atom, these interactions are extremely weak. So comparing our four answer choices, hydrogen bonding is significantly stronger than dipole-dipole interactions and London dispersion forces, meaning the correct answer is A. The second question asks, which of the following has the weakest intramolecular force? So this question is specifically asking about intramolecular forces, which means we're analyzing the strength of the covalent bonds within each individual molecule rather than interactions between molecules. So to answer this, we need to compare the types of covalent bonds or ionic bonds present in each compound. We start off with C2H2. This molecule contains a triple bond between the two carbon atoms. Triple bonds are the strongest type of covalent bond because they involve more shared electrons, and that makes the molecule more rigid and difficult to break. The only other intramolecular interaction that's stronger than a triple covalent bond is going to be our ionic bond. Now, B says C2H4. This molecule contains a double bond between the two carbons. Double bonds are weaker than triple bonds, but stronger than single bonds. Then we have C2H6. In this molecule, there is only a single bond between the two carbon atoms and only single bonds between the carbons and hydrogens. And finally, we have carbon dioxide. This molecule consists of two double bonds between carbon and oxygen. These are stronger than single bonds, but weaker than triple bonds. So since the question is asking for the weakest intramolecular force, we look for the molecule that contains only single bonds because single bonds require the least amount of energy to break. And that makes the correct answer choice C. So far, we can say that we've discussed intermolecular forces broadly, but now we're going to focus on three in particular: dipole-dipole interactions, hydrogen bonding, and London dispersion forces. Let's begin with dipole-dipole forces. Like we mentioned earlier, these forces occur between polar molecules, meaning they have permanent dipoles. These are regions where one side of the molecule is partially positive and the other is partially negative. And this arises due to differences in electronegativity between bonded atoms. Electronegativity is a measure of an atom's ability to attract electrons in a bond. When two atoms with different electronegativities form a bond, the more electronegative atom pulls the electron density more towards itself and it gains a partial negative charge. Then the less electronegative atom, it's going to lose some electron density, and that results in a partial positive charge. These partial charges drive dipole-dipole interactions. The partial positive end of one molecule is attracted to the partial negative end of another, and that creates an intermolecular force called a dipole-dipole interaction. Of course, the strength of dipole-dipole forces depends on the magnitude of the dipole moment, which is determined by the difference in electronegativity between the bonded atoms. A larger electronegativity difference creates a stronger dipole moment, and that leads to stronger dipole-dipole interactions. In short, greater molecular polarity results in stronger dipole-dipole forces. A great example is hydrogen chloride. Since chlorine is much more electronegative than hydrogen, it creates a strong dipole where the partial positively charged hydrogen end of one hydrogen chloride molecule is attracted to the partially negative end of a chlorine atom in another hydrogen chloride molecule. And this intermolecular attraction helps keep hydrogen chloride molecules close together in the liquid and solid phases. So the key takeaway here is that dipole-dipole forces only exist between polar molecules. Now that we've covered dipole-dipole interactions, let's move on to a stronger and more specialized type of dipole interaction. That's hydrogen bonding. Hydrogen bonding is one of the most important intermolecular forces with significant effects in both chemistry and biology. Hydrogen bonding plays a crucial role in water's unique properties, the structure of DNA, and even why certain substances dissolve in others. Hydrogen bonding occurs when a hydrogen atom is directly bonded to one of three highly electronegative atoms. Those are fluorine, oxygen, or nitrogen. These atoms pull electron density strongly towards themselves, leaving the hydrogen with a significant partial positive charge. This highly polarized hydrogen is then attracted to the lone pairs on a fluorine, oxygen, or nitrogen atom in a neighboring molecule, and in this manner, it forms a hydrogen bond. So for hydrogen bonding to occur, two key conditions must be met. We need a highly polarized hydrogen atom in one molecule, meaning hydrogen must be directly bonded to fluorine, oxygen, or nitrogen. And then we need a lone pair on a fluorine, oxygen, or nitrogen atom in another molecule, which acts as the hydrogen bond acceptor. Now, water is an excellent example of hydrogen bonding in action. Each oxygen atom has two lone pairs, and that allows a single water molecule to form hydrogen bonds with multiple others. And this extensive hydrogen bond network is responsible for water's high boiling point, surface tension, and ability to remain a liquid over a wide temperature range. Another great example is hydrofluoric acid, where fluorine's high electronegativity creates a highly polarized hydrogen-fluorine bond. The partial positive hydrogen on one hydrofluoric acid molecule is strongly attracted to the partial negative fluorine on another, and in this manner they form strong hydrogen bonds. However, unlike water, each hydrofluoric acid molecule can only form one hydrogen bond, so that limits its hydrogen bond network. Now we want to discuss hydrogen bonding and its effect on boiling point. Since boiling point is directly related to the strength of intermolecular forces, hydrogen bonding has a significant impact on how substances behave when they're heated. So to better understand this, let's first define what boiling point actually means. The boiling point of a substance is the temperature at which its vapor pressure equals the external atmospheric pressure. And that's going to allow molecules to escape from the liquid phase into the gas phase. So in simple terms, boiling occurs when molecules have enough kinetic energy to overcome intermolecular forces and separate from one another. The stronger the intermolecular forces, the more energy is required to break those attractions, and that results in a higher boiling point. If we only consider London dispersion forces, we would expect that boiling point would follow a predictable trend as we move down a group in the periodic table. Larger atoms, they have more electrons, which makes their electron clouds more polarizable. And that means that it would lead to stronger London dispersion forces and consequently higher boiling points. And that's exactly what we see with group 14 hydrides, where the boiling point smoothly increases as you move down the group. However, the hydrides of groups 15, 16, and 17 break this pattern. Instead of showing a smooth increase in boiling points, the first member of each group, ammonia, water, and hydrofluoric acid, they have much higher boiling points than expected. Their boiling points are higher than the other hydrides in their respective groups that are shown in this figure. What is responsible for this? The answer is hydrogen bonding. Unlike group 14 hydrides, which rely only on London dispersion forces, ammonia, water, and hydrofluoric acid, they experience hydrogen bonding, and that significantly raises their boiling points beyond what we would predict based on molecular size alone. Now, between these three, ammonia, hydrofluoric acid, and water, how do their boiling points compare? Let's start with ammonia. Ammonia can form up to 3 hydrogen bonds per molecule since nitrogen has 1 lone pair and 3 hydrogen atoms available for bonding. However, the electronegativity difference between nitrogen and hydrogen is only 0.9, meaning its individual hydrogen bonds are weaker than those in hydrofluoric acid or water. This gives ammonia a higher than expected boiling point, but it is still lower than both hydrofluoric acid and water. Hydrofluoric acid, it has the largest electronegativity difference of 1.9 between the hydrogen and fluorine atom. So that makes its individual hydrogen bonds very strong. However, each hydrofluoric acid molecule can only form one hydrogen bond since fluorine has only one hydrogen atom attached. This results in strong but limited hydrogen bonding, and it causes hydrofluoric acid's boiling point to be higher than expected, but still lower than water's. Water combines both factors. It has a strong electronegativity difference of 1.4, and it has multiple hydrogen bonds per molecule. Each water molecule can form two hydrogen bonds, and that allows it to create an extensive hydrogen bonding network that holds water molecules together more effectively than ammonia or hydrofluoric acid. So as a result, water has the highest boiling point of the three, and it makes it the strongest example of hydrogen bonding among these three molecules. Now that we've discussed how hydrogen bonding impacts boiling points, let's apply what we've learned to a couple of concept check questions. The first question asks, based on the graph of hydride boiling points, which of the following statements is true? Let's go through each choice carefully. A says, the hydrides that exhibit hydrogen bonding are in N equals 5. This statement is incorrect because the hydrides that exhibit hydrogen bonding, ammonia, water, and hydrofluoric acid, they're all found in N equals 2, not N equals 5. The N equals 5 hydrides, they follow normal London dispersion force trends rather than hydrogen bonding effects. And we can see that directly from our graph. So that first statement is incorrect. Let's read answer choice B. Answer choice B says there are 3 hydrides that exhibit hydrogen bonding. And this statement is correct. Based on the graph that we introduced in this lecture, there are 3 hydrides that exhibit hydrogen bonding, and they are ammonia, water, and hydrofluoric acid. This is the correct answer, but we're still going to work through C and D. C says dispersion forces causes a linear increase in boiling point as you move up the periodic table. This is incorrect because dispersion forces do cause a linear increase in boiling point, but it's only as you move down the periodic table, not up. Larger atoms have stronger London dispersion forces, which increases the boiling point. So this statement is incorrect. D says boiling point decreases with increasing intermolecular forces. This statement is false because boiling point actually increases with stronger intermolecular forces, not decreases. A substance with stronger intermolecular forces requires more energy to separate the molecules, and that leads to a higher boiling point. So this statement is also incorrect. The correct answer for this problem is B. The second question asks, which of the following is false about hydrogen bonding? Let's analyze each statement carefully. This first one says, ammonia has stronger hydrogen bonding than water because it can make 3 hydrogen bonds. Now, while ammonia can form up to 3 hydrogen bonds per molecule, the individual hydrogen bonds in ammonia are weaker than those in water. And this is because the difference in electronegativity between nitrogen and hydrogen is smaller. It's 0.9 compared to the electronegativity difference between hydrogen and oxygen in water, which is 1.4. So while ammonia has more potential hydrogen bonding sites, The strength of each hydrogen bond matters more than just the number. So this statement is incorrect. So A is the correct answer choice for this problem because we're looking for a false statement. But let's still work through B, C, and D. B says hydrofluoric acid is the only molecule that can form hydrogen-fluorine hydrogen bonding. This statement is true. Hydrofluoric acid is the only molecule that can exhibit hydrogen-fluorine hydrogen bonding because fluorine is the only element that can form a highly polarized HF bond that's strong enough to create hydrogen bonds. C says the difference in electronegativity is an important factor in determining the strength of a hydrogen bond. This is also true. The electronegativity difference between atoms in a hydrogen bond determines how strong the attraction is. A larger electronegativity difference creates a stronger dipole, which in turn leads to stronger hydrogen bonding. Then finally, D says water has a stronger hydrogen bonding force overall than hydrofluoric acid. This is also true. Water has stronger hydrogen bonding forces than hydrofluoric acid because each water molecule can form 2 hydrogen bonds, and that allows it to create a more extensive hydrogen bonding network than hydrofluoric acid, which can only form 1 hydrogen bond per molecule. So statements B, C, and D are true. The only false statement here is answer choice A. Now that we've covered dipole-dipole interactions and hydrogen bonding, we need to focus on London dispersion forces, also known as van der Waals forces. This is the weakest type of intermolecular force, but it's present in all molecules, whether they are polar or non-polar. Even though London dispersion forces are weak, they are still extremely important, especially for non-polar molecules, because they are the only forces holding them together in the liquid and solid states. So what exactly are London dispersion forces and how do they work? London dispersion forces arise from temporary induced dipoles. So at any given moment, the electrons within an atom or molecule, they're constantly moving. This means that for a brief instant, the electron distribution can become uneven, and that creates a temporary dipole, which is a region of slight positive and slight negative charges. This temporary dipole can then induce another dipole in a neighboring molecule, and that causes a momentary electrostatic attraction between 2 molecules. Because these dipoles are constantly moving, forming, and disappearing, London dispersion forces are weak and short-lived. So unlike dipole-dipole interactions, which occur between molecules that have permanent dipoles, London dispersion forces exist only due to the random movement of electrons, meaning their strength depends entirely on how easily the electron cloud can be distorted. This is a property called polarizability. Larger molecules experience stronger London dispersion forces. The larger the electron cloud, the easier it is to distort, which means the easier it is to create a strong temporary dipole. This is why boiling points increase as molecules get larger, even in nonpolar substances. In addition, London dispersion forces increase with molecular shape. So straight chain molecules are going to have stronger London dispersion forces than branched ones because they have more surface area for intermolecular interactions. Since we now know the 3 main types of intermolecular forces for Gen Chem 1, hydrogen bonding, dipole-dipole interactions, and London dispersion forces, we need to understand how to determine which forces are present in a molecule. So here's a simple decision process. The first question you want to ask is, does the molecule have a hydrogen-fluorine, a hydrogen-oxygen, or a hydrogen-nitrogen bond? If the answer is yes, then the forces that are present are hydrogen bonding, which are the dominant forces, and London dispersion forces, because London dispersion forces are always present. If the answer is no, though, then you move on to the next question. Is the molecule polar? If the answer is yes, then the molecule experiences dipole-dipole forces and London dispersion forces. If the answer is no, then the molecule only experiences London dispersion forces. So for example, if we look at water, the first question we want to ask is, does the molecule have any HF, HO, or HN bonds? And the answer to this is yes. There is oxygen-hydrogen bonds present in water. So the intermolecular forces at play here are going to be hydrogen bonding and London dispersion forces. What if we had chloromethane, CH3Cl? For the first question, does the molecule have any HF, HO, or HN bonds? The answer would be no. Then we ask, is the molecule polar? Here the answer is yes. So that means the intermolecular forces at play are dipole-dipole forces and London dispersion forces. Finally, if we were to look at a molecule like methane, CH4, the answer to the first question would be no, and so would the second question. The second question would also be no. This is non-polar. So that means the only intermolecular forces at play here for methane are London dispersion forces. Now we're going to take all of this information, we're going to apply it to a couple of practice problems. This first one says, which of the following is true regarding dispersion forces? Let's go through each answer choice carefully to determine which one is correct. Answer choice A says they occur due to permanent dipoles. This is incorrect because dispersion forces arise from temporary induced dipoles, not permanent dipoles. Permanent dipoles are responsible for dipole-dipole interactions, not London dispersion forces. So this statement is false. B says they are stronger in smaller molecules. This is also incorrect. London dispersion forces are actually stronger in larger molecules because larger electron clouds are more easily distorted. So that increases the polarizability and the strength of the dispersion forces. So B is also incorrect. C says they are formed symmetrically around the molecule. This is incorrect because London dispersion forces arise from random electron movement, which leads to temporary fluctuating dipoles. They're not symmetrical or evenly distributed, so false. D says they are the dominant intermolecular force in nonpolar molecules. This is correct. Since nonpolar molecules do not have permanent dipoles, they cannot experience dipole-dipole forces or hydrogen bonding. Instead, London dispersion forces are the only intermolecular forces that are present and are therefore the dominant intermolecular force in nonpolar molecules. So the only true statement is D. The next problem says, which of the following molecules will have the strongest dipole-dipole forces? To determine the strongest dipole-dipole forces, we need to identify which of these molecules is the most polar, since dipole-dipole interactions depend on the magnitude of the dipole moment. In other words, the larger the electronegativity difference, the stronger the dipole-dipole force. When we look at our answer choices, we notice that all of these molecules are polar because they contain a carbon-halogen bond, where the halogen is chlorine, bromine, iodine, and fluorine. Now, the strength of the dipole-dipole force, again, depends on the electronegativity difference between carbon and the halogen. We know from previous lectures that fluorine is the most electronegative element, meaning it creates the largest dipole moment in molecule D, and that makes it the molecule with the strongest dipole-dipole interaction. We also know that as we move down the halogen group, electronegativity decreases, So that means the dipole moment also decreases. So the correct answer is D, because fluorine creates the largest dipole moment, leading to the strongest dipole-dipole interactions. Now for our final problem, this one asks, which of the following statements are true about intermolecular forces? Let's read each answer choice. A says, as intermolecular forces increase, the boiling point of the molecule increases. Now, this statement right off the bat is the true statement. Boiling point is directly related to intermolecular forces because a substance boils when its molecules have enough energy to overcome intermolecular attractions and transition into the gas phase. Stronger intermolecular forces require more energy to break, leading to higher boiling points. We're still going to read B, C, and D. B says, as intermolecular forces increases, the boiling point of the molecule decreases. This is incorrect for the reasons that we just stated. C says the intermolecular force strength of a molecule does not affect the boiling point. This is also false. We just said that there is a direct relationship. As intermolecular forces increase, the boiling point of the molecule also increases. Finally, D says hydrogen bonding can only occur between oxygen and hydrogen. This is also a false statement because hydrogen bonding occurs between hydrogen and 3 highly electronegative elements, which are fluorine, oxygen, and nitrogen. So with that being said, the correct answer for our final problem is A. And with that, we've completed our lecture. I hope this has been helpful. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day.